interval on the mean, you compute m, the mean of a sample, in order to estimate mu, the mean of the population. Clearly, if you already knew the population mean, there would be no need for a confidence interval. However, to explain how confidence intervals are constructed, we're going to work backwards and begin by assuming characteristics of the population. Then, we will show how sample data can be used to construct a confidence interval. Assume that the weights of 10-year-old children are normally distributed with a mean of 90 and a standard deviation of 36. What is the sampling distribution of the mean for a sample size of 9? The mean of the sampling distribution of the mean is the population mean, mu. The standard deviation of the sampling distribution of the mean is the standard deviation of the population divided by the square root of the sample size. This standard deviation is called the standard error of the mean. We use sigma to refer to the population standard deviation, sigma sub m to refer to the standard error of the mean, and n to refer to the sample size. In this example, the sampling distribution of the mean has a mean of 90. The standard error is the population standard deviation of 36 divided by the square root of 9. That is, 36 divided by 3, which equals 12. The sampling distribution is shown here. The shaded area represents the middle 95% of the distribution and stretches from 66.52 to 113.48. These limits were computed by adding and subtracting 1.96 standard deviations from the mean of 90 as follows. 90 minus 1.96 times the standard error of 12 equals 66.52. 90 plus 1.96 times 12 equals 113.48. The value of 1.96 is used because 95% of the area of our normal distribution is within 1.96 standard deviations of the mean. This figure shows that 95% of the means are no more than 23.48 units, or 1.96 standard errors, from the mean of 90. Now consider the probability that a sample mean computed in a random sample is within 23.48 units of the population mean of 90. Since 95% of the distribution is within 23.48 of 90, the probability that the mean from any given sample will be within 23.48 of 90 is 0.95. This means that if we repeatedly compute the mean, m, from a sample, and create an interval ranging from m minus 23.48 to m plus 23.48, 95% of these intervals will contain the population mean of 90. In general, you compute the 95% confidence interval for the mean with this formula. Z sub 0.95 is the number of standard deviations extending from the mean of a normal distribution required to contain 0.95 of the area. Sigma sub m is the standard error of the mean. If you look closely at this formula for a confidence interval, you will notice that you need to know the standard deviation of the population. You may think this sounds unrealistic, and you'd be right. However, computing a confidence interval when the standard deviation of the population is known is easier than when the standard deviation of the population has to be estimated. So we'll do the easier version first, since it will help us understand how to do the harder but more useful version. Later, we will show how to compute a confidence interval when we have to estimate the standard deviation of the population. The 5 numbers shown were sampled from a normal distribution with a standard deviation of 2.5. To compute the 95% confidence interval, start by computing the mean and standard error. The mean equals 5. The standard error equals 2.5 divided by the square root of 5, since n equals 5, and is equal to 1.118. Z sub 0.95 can be found using the normal distribution calculator. You specify that the shaded area is 0.95 and indicate that you want the area to be between the cutoff points. As shown here, the value is 1.96. If you had wanted to compute the 99% confidence interval, you would have set the shaded area to 0.99, and the result would have been 2.58. The confidence interval can then be computed as shown. The lower limit equals 5 minus 1.96 times 1.118, which equals 2.81. The upper limit equals 5 plus 1.96 times 1.118, which equals 7.81. When the standard deviation is not known but has to be estimated from sample data, you should use the t-distribution rather than the normal distribution. When the sample size is large, say 100 or above, the t-distribution is very similar to the standard normal distribution. However, with smaller sample sizes, the t-distribution is leptokurtic. Leptokurtic means there are relatively more scores in its tails than the middle of the distribution relative to the standard normal distribution. This figure shows a comparison of the t-distribution you would use with an n of 5 and the standard normal distribution. The t-distribution is the one in blue. It is lower in the middle, but is higher in the tails. Here is a close-up of the t-distribution that shows the tails clearly. Recall that with a normal distribution, 95% of the distribution is within 1.96 standard deviations of the mean. In this t-distribution, 95% of the distribution is within 2.78 standard deviations of the mean. Therefore, when computing the 95% confidence interval with a sample size of 5, you multiply the standard error of the mean by 2.78 rather than 1.96. The values of t to be used in a confidence interval can be found using the inverse t-distribution calculator, or can be looked up in a table of the t-distribution. A small version of a t-table is shown here. The first column, df, stands for degrees of freedom, and for confidence intervals on the mean is equal to n-1, where n is the sample size. For example, the t for a 99% confidence interval based on 9 subjects would have 8 degrees of freedom and would be 3.355. The 5 numbers shown here were sampled from a normal distribution. The first steps in computing a confidence interval are to compute the sample mean and the variance. The mean equals 5, and the variance equals 7.5. The next step is to estimate the standard error of the mean. If we knew the population standard deviation, we could use the formula shown here, where sigma sub m is the standard error of the mean, and sigma is the standard deviation of the population. The standard error of the mean equals the standard deviation of the population divided by the square root of n. Since we don't know the standard deviation in the population, we use the sample standard deviation to compute an estimate of the standard error. S sub m is the estimated standard error of the mean, and S is the sample standard deviation. In this example, the estimate of the standard error of the mean is equal to 1.225. The next step is to find the value of t. The degrees of freedom equals n-1, which in this example is 4. As you can see from the table, the value for the 95% interval for 4 degrees of freedom is 2.776. The confidence interval is then computed in much the same way it is when we know the standard error of the mean. The only differences are that the estimated standard error of the mean and t are used rather than the actual standard error of the mean and z. The lower limit equals 1.60 and the upper limit equals 8.40. The general formula for the confidence interval on the mean is shown here. M is the sample mean, T sub CL is the t for the confidence level desired, and S sub m is the estimated standard error of the mean.